We are now looking at the teaching video on indices. So for point 1, when we are looking at bases and indices, given this expression here, a to the power of n, then a is the base. And then n would be the index. So we can see the spelling of the plural form of index is indices. Point 2, we are looking at some rules of indices. So we classify it this way such that you would be able to recall systematically. Of course, when you memorize them, will be just as systematic as well. So for the point A, we have same basis. You can see part 1, A, same basis. Part 2, A. But these two parts involve, first of all, here multiplication, here division. So this is how we memorize all the rules. Same basis, multiplication or product. Then we have a to the power of the sum of the two indices. Same basis, but quotient or division. Then we have a to the power of the difference of the two indices. Next, we look at, in part B, same indices. Part 1, m, same indices. Part 2, m, and this should be m, same indices. But in the part 1, we have product. Part 2, we have quotient, multiplication, division. So we have here a times b to the power of m. Next, in part 2, we have a divided by b to the power of m. So for part C, where we are looking at negative indices, you can see part 1, negative m as the index, part 2, negative m as the index. So for part 1, a to the power of minus m is a numerator. Therefore, I'll take the reciprocal of that, but without the negative sign for the index. As for part 2, I will also take the reciprocal of this. So it's 1 over the reciprocal of a to the power of m without the negative sign. And therefore, I will have a to the power of m. In other words, to make it simple to remember, numerator, denominator without the negative sign for the index. Denominator, numerator without the negative sign for the index. So part D, we are looking at the roots. So for this, we have the square root of a. For this, we have the cube root of a. And for this, we have the nth root of a to the power of m. So for the part 1, we have a to the power of half. For part 2, we have a to the power of 1/4. method, you can see there is a little 3 here, so the denominator of the fractional index is a 3 here. Here we don't have a 2, but the denominator of the fractional index is 2. Over here, in part 3, we have the nth root. So basically, we have n in the denominator of the fractional index, then m as the numerator. Now we look at part E, 0 or unit integers. So in part 1, we have a to the power of 0. So that will give me a 1. So in fact, any number to the power of 0 is 1. So part 2, a to the power of 1, that will just be a. For part F, we have this arrangement, a to the power of m, bracket, raised to the power of n. So in this case, you have integers separated by just a bracket. We have, for the result, a to the power of m times n. So when we remember the rules of integers, we think in terms of perhaps same bases, same integers, negative roots, negative integers, roots, and these special names that we have given to you, so that it's easier to categorize them and then recall them systematically. There are also important results that we have to bear in mind. These are some of them. So for the first one, we have the algebraic expansion. So basically, the formula would be a squared plus 2 times a times b plus b squared. So there are 2 terms in the bracket here. So the first 2 sets of the bracket, I'll put in a, the first term in the bracket, and then the next 2 sets of bracket, I'll put in the second term. As for part B, it will be just like this expression, except that the first sign here in part A is a plus, in part B will be a negative. So I will have a squared minus 2 times a times b plus b squared. Next, this is a case of difference of 2 squares. We know it by this. The first terms in the 2 sets of brackets are the same. The second term in the 2 sets of brackets are also the same. The only difference is this. In the first set of bracket, we're looking at the difference. The second set of bracket, we're looking at a sum. So the difference of 2 squared is this. A squared minus b squared. First term in the first set of bracket, second term in the second set of bracket. For part D, I can just give you this identity. Negative a, negative b, bracket raised to the power of 2 is the same as a plus b bracket squared. But I would show you why this result is true. Let's begin with negative a minus b squared. I can take out the common factor of negative 1. Then in the bracket, I will have a plus b, and the square is on the outside. So what I've chosen to do is to deal with what's inside the bracket first. Factorize the minus 1 out of that expression. So now squaring the negative 1. Squaring the negative 1, I'll get a 1. Then squaring the a plus b, I'll just get a plus b squared. Hence, this result. Of course, this will expand to the same result as I have over here. Next, for part E, I have bracket ax bracket squared. So this square is for the a as well as for the x. So I would have a squared x squared. Now we continue with other important results. For part F, we have bracket negative ax bracket squared. So the negative 1 is inside the bracket that is squared. So negative 1 squared is just 1. Then I have a squared and x squared. For G, I have a times negative bx. I have a positive expression multiplied to a negative expression. I have a negative expression. Then a times bx. So a bx. Next, I have a negative expression multiplied to a negative expression. I will have a positive expression. So the result then would be a times bx. A bx. Now we look at the use of integers in simplifying algebraic fractions. I have here 3 cases, but the approach that I would show you is not the messy approach that just do cancellation everywhere. By doing cancellation like that, it will actually confuse the marker because there are too many markings everywhere. So the important thing to note is how then can we present such type of simplification. So the best way is still to go back to the use of integers. So for part A, I have 125 x y cubed times z divided by bracket 2xy z cubed bracket squared times 64 x power 5 times y times z to the power 4 over 5 squared times x times yz, y cubed times z. So the first thing to do is to actually open up all the brackets. So 125 x y cubed times z over 2 times 2 or 2 squared is just 4. Then I have 1 here, x to the power 1 squared, so x squared. Then y squared, then z, 2 times 3, 6. Over here, for the numerator, I have the same expression. For the denominator, I have 5 squared, so that it will be 25. So pull the number part to one side, 125 times 64 over 4 times 25. Next, I'll deal with all the x terms together, x to the power of 1, because it's times, so I add on to the index here, plus 5. Now we are looking at the denominator, so divided by, so minus the 2, minus the 1. Then y to the power of 3 times, I'm looking at adding to this 1, divided by minus the 2, minus the 3. Then z to the power 1 times, so I add on to the 4, divided by, so minus the 6, minus the 1. So here, for this particular part, I can actually use the calculator. So 125 times 64 divided by 4 divided by 25, I have 80. So 80 x to the power of 1 plus 5 is 6, 6 minus 2 is 4, 4 minus 1, 3. 3 plus 1, 4, minus 2 is 2, 2 minus 3 is just minus 1. Z, so 1 plus 4 is 5, 5 minus 6 is minus 1, minus 1 is minus 2. Now where I have the negative integers, I will take the reciprocal of that and then remove the negative sign. So I have 80x cubed over y times y squared. So this is how I have avoided just cancelling and confusing the marker and even myself. So for part B, (225) x squared y to the power of 4 z to the power of 6 times 1 over 15 times x y z to the power of 2. So whenever we have the square root of 225 is just 15. But when we look at the integers here, because of the square root, I will just half it. So half of the 2 is 1, half of the 4 is 2, half of the 6 is 3. Now the 15 divided by 15 is just 1. X times x is x squared. Z squared times z will be, or y squared times y is y cubed. Z cubed times z squared is z to the power of 5. So sometimes we don't have to write it in this way if it's simple enough to do the computation for the integers. C. 7 to the power of n plus 1 minus 7 to the power of n over 7 to the power of n plus 2. So far, in part A, what we have done is we try to separate the numerical part from the variable part. And for the variable part, we use integers rules to simplify. In part B, when we deal with the square root, then in this particular case, we just halve all the integers for the variable part. Now, and we also can do this mentally because it's less involved than, say, those type of questions in part, like part A. In part C, to simplify this, I will have to look at the rule of indices the reverse way. Where I group, now I have to split up. So the integers here, I have n plus 1 and n plus 2. So when I think of the index n plus 1, I can have 7 to the power n times 7 to the power 1 minus 7 to the power n. Here in the denominator, I would have 7 to the power n times 7 squared. So taking out common factors, I would have 7 to the power n times the 7 minus the 1. If I take this 7 to the power n as a factor, then I'm left with the universal factor 1 divided by 7 to the power n times 7 squared. In this case, you can actually do a little cancellation here, just like that. And for the numerator, 7 minus 1 is just 6. And for the denominator, 7 squared is 49. So from here, I've simplified the expression to just a rational number. So for this teaching video, you have actually looked at the rules of integers plus some important results and also some ways to make simplification of any expression involving integers simpler. So we have come to the end of the video.